Hey everyone, today we will be deriving the Policy Gradient Theorem and then implementing the reinforce algorithm that actually uses it. Right, so this can be a little bit of a long video. I'd recommend just chunking it up and taking it at your own pace. But let's go ahead and get started. So let's remind ourselves again, what have we done in all of the previous reinforcement learning algorithms that we looked at? Let's take Q-learning, for example. The entire purpose of Q-learning is for our neural network to estimate Q values. And what that meant is at every single state, we learn some number that represents the Q value of that action taken at that state, right? So at this state, these are my Q values for the three different actions I could take. At this state, these are the three different Q values I could take at that state, so on and so forth. Or three different Q values for the actions I can take at that state, so on and so forth. And after we've learned this, what do we do? What do we actually want? The entire point is to derive our policy. The policy is what prescribes what action do I take at a state. I don't really care about the Q values. It's just the Q values is the way we derive our policy. So once we've computed our Q values, we can then go back and select what is the action with the highest Q value. So our policy is derived from that. So this is basically a greedy method, right? Just select the action that had the highest Q value. Whatever our neural network says has the highest Q value. And that's it, right? So the Q values are kind of just this middleman, right? We compute these Q values, but in the end, we don't actually care about the Q values. We just care about the max Q value. And in deep Q learning, right, it was exactly the same thing. We had instead of having a table, we had a neural network, but the neural network took some state features. It predicted some Q values for the different actions, and then we selected the action with the highest Q value, and that's all that we did. But what we want is the policy. Right? What we want is the policy, not the Q values. We just care about the policy. So the question is there a way to avoid the Q values altogether? Can we just update our policy? To do this, there is one light prerequisite that you've heard of stationary distributions. We'll just give a quick idea of what a stationary distribution is. A stationary distribution is essentially if we start at some node and randomly move around for as long as you want, what is the probability at being at the different states, right? That's basically what it is. So in any Markov chain, in any system, we probably have these transition probabilities, right? What's the likelihood of transitioning from one state to another state, so on and so forth. And basically, if I'm starting at, let's say, B, I have a 30% chance of going to C, 10% chance of going to E, 40% chance of going to A. Okay, so let's say we take a step and we happen to go to C. And then from C, we have a 30% chance of going back to B or a 20% chance of going to D, 10, whatever it may be, right? We have all of these transitions. And you can imagine if we start somewhere and just kind of randomly move around, so a common question could be if I move around, let's say 1,000,000 times, move around a bunch, what's the probability that I'll end up at D or at E or at C or at A? Or just end up back at B again. It doesn't matter. So the stationary distribution is exactly that. What is the probability at being at a state after a bunch of essentially iterations? And there's a bunch of ways you can compute this. So this is a quick GIF that I made where we start basically randomly at every, so if there's 5 states, 20% likelihood everywhere. As we keep taking more and more iterations, you'll start to see the transition probabilities, or sorry, your state probabilities start to converge. And you can see that it converges to, this is about a 25.6% chance being at state 2, a 20% chance being at state 1, 17% chance, 18% chance being state 4, so on and so forth. And so this is our stationary distribution, right? The likelihood at being at every single state. Computing this is relatively straightforward. There's actually 2 different ways of doing it. The first one is we set up our transition probability matrix like this, and that's how I created this visual. And let's say we start at 20% probability at every state. So if there's 5 states, that's random, right? We're randomly selecting to be at any one of them uniformly. And then we just apply that transition probability matrix to our distribution here. So basically we go from 0.2, 0.2, 0.2. We apply the transition probabilities to my starting probabilities, and that gives me this. So after I apply one step of transition, you can see that we're still 20% likely to be at the first state, 24% likely to be the second state, 24% likely to be the third state, so on and so forth. But If we keep doing this over and over and over again, do a bunch of iterations, you'll see that we'll essentially just converge, right? We'll converge to these probabilities. And these probabilities are our stationary distribution, right? What is the probability of being at a state given that you just take a bunch of steps through this system? There's another way of doing it. You can essentially solve the system of equations. Basically, if pi is equal to pi times my transition matrix, then that's the same thing, right? So the cool thing about a stationary distribution is if you take the stationary probabilities, right, like these values here, and multiply them by your transition probabilities, well, you should get the same values on the other end because it's the stationary distribution. You shouldn't keep changing as you apply that same transition probability matrix. And so if we apply it, you can kind of just solve the system, right? Just simple linear algebra, and you can just, solve, and you'll get exactly the same stationary distribution. Nothing fancy. But that's it. That's all I want to go into about stationary distributions. The main thing you need to keep in mind is that a stationary distribution is one that represents what's the probability of being at a specific state given that you've kind of randomly moved around the system for a while. And that's all. So what is it that we want to maximize? So coming back to reinforcement learning, what is the thing that we want to maximize? We want to maximize the value of all the different states in our environment, right? We have all these different states, and what we want to do is maximize the value, right? Maximize our future expected returns for that specific state. That's always been the case. But the question is, well, I want to maximize all the states, but what actually matters is not just the value of those states, but also how likely am I to be in that state? And this is where the stationary distribution comes. The stationary distribution tells me what is the probability of being at some specific state S. And then the value tells me what is the value of that specific state. So what I really want to maximize is this entire system. And just to be very clear, the derivation we're doing is coming from an awesome blog post from, let me just double check, Lillian Wang. So awesome blog post. I will be linking these down below. And you can also look in the Sutton and Bardo textbook, just look up Policy Gradient Theorem, and it'll be like the very first thing that shows up in the table of contents. You can take a look at that. So the derivation we're about to do is going to be very, very close to those. That's where I got it from, right? There's not too many different ways of solving for these things anyway. So getting back to this, so we want to maximize, right? Our cost function is we want to maximize the value of a state times the probability of actually being at that state to begin with. And that's all. And so now that we have that, we have a little bit of an issue. And we need to compute, right? If we're doing a neural network, essentially, this is our cost function or loss function. And if we have a loss function, we need to take the derivative of the loss function. So here we go. We need to take the derivative of j theta, no problem. And that should be easy, right? So if I want the derivative of j theta, well, it's the derivative of this thing that I just wrote, and we can just rewrite that. We know the Bellman equation. From the Bellman equation, the values is really just the weighted sum of our actions, right? Weighted sum of the actions. So we can rewrite the values as this, and there we go. The derivative of the cost function is just the derivative of the sum of our stationary distribution times the sum over the actions of all this stuff. I'm also expecting that you already know the derivation of the Bellman equation. I have a video of that from earlier, or you're just comfortable with the Bellman equation. I'll link all that down below as prerequisites just so you can take a look at that if you're not sure. But as we keep going, what do we do with this? How did we just compute the stationary distribution? Well, the stationary distribution depends on the policy, right? The policy decides what action do we take at every single state. So the policy kind of decides that transition matrix, right? How we transition between the different states kind of depends on the policy that we've selected. And the problem now becomes, if I need to take the derivative of all of this, I need to somehow evaluate this. And we saw two ways of doing it, right? You can iteratively solve for it, or you can use the, you can do a inverse, a least squares method as well to solve for it. And both of those would be fine, except every single time my policy changes, then I have to recompute my stationary distribution for the new policy. And this is kind of impractical already. What makes it even more impractical is the example I showed with the Markov states assumes that there's 5 different states, right? Like there's a discrete number of states that we can be in. But as we've seen with interesting environments like the like the cart pole game or the lunar lander game that we've been looking at, your states are not discrete, they're continuous. You have a continuous representation that tells us about the state. So how do we compute the stationary distribution over a continuous distribution? It'd be impossible, right? Because we have basically a continuous Markov chain, and this is no longer a feasible thing for us to compute. And so, and even on top of that, we don't actually care about the stationary distribution, but rather its derivative, which is just another level of complexity. And so the policy gradient theorem, our entire focus is going to be how can we compute the derivative of this without actually computing the derivative over the stationary distribution. And that's the trick. So this is the derivation we're going to get to. So let's go ahead and just start. This is a little bit long of a derivation, nothing too complicated, but it is a little bit long. So we'll kind of start working through it. But this is our target goal. And we'll see where all of this comes from. So let's open this up. All right. Driving is fun. So yeah, go ahead, grab a pencil, follow along, and we will get through this just fine. Let's write down our starting point again. The starting point was essentially we wanted the derivative with respect to the parameter theta, right, of the neural network, whatever we're using, j theta, and that's going to be the derivative of theta, and it's going to be the sum over the states of our stationary distribution, right? So what is the probability at being at the state according to our stationary distribution? And then we're going to have another sum over the actions, and we'll have pi theta a given s, and then we will have our q. And actually, before we even write any of this, let's just keep it simple. We're just going to write the original statement, which was v pi s. And that's what we had, right? This is what we want to take the derivative of. And like I mentioned, taking the derivative of this is kind of impossible because we'd have to recompute the stationary distribution over and over again. So let's go ahead and just do a little bit of a simplification. Instead of computing the derivative of all of this stuff, let's just focus on the derivative of this, right? Just the values alone. Let's just focus on this for now, and you'll see how the problem unfolds as we explore it, right? So let's go ahead and start there. So you want to compute the derivative with respect to the parameters of our value function, right? The value function alone. And that's pretty easy, or not easy, that's what we're going to be working on, but that's what we're going to start pulling apart essentially. And we know that the values, according to the Bellman equation, is a weighted average, right? Weighted sum of our Q values, right? The values are basically, the values are just a state, are the states, and the values are basically just a marginal of the Q values, right? So we just essentially just sum over them. So let's go ahead and do that. The values can be written as the sum over the actions of the probability of taking some action at some state. And this is determined by the policy, so it's of the neural network. And then Q pi SA, right? So there we go, state action. Good. So that's our first step. And now by standard, if we're taking a derivative, we need to do the, we're doing the derivative of the product of two different things. So we have to do the product rule, and the derivative of a sum is the sum of the derivative. So we can rewrite this as this is equal to the sum over the actions. And there's going to be a really big bracket around everything, but just know that this sum here applies to everything inside. But for now, it's fine. It's going to be the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing, right? So that's the standard product rule. So we'll do the derivative of theta, pi theta a given s, and then this is just going to stay the same, q pi s a. So this gradient applies only to this first term right here. And then plus, we're going to do the same thing, right? So it's going to be the other way around. So it's going to be pi theta for some action given state times the gradient of our q value for some state action pair. And that's it, right? That's our standard, right? The derivative, if you do the derivative of b times a, that's b prime a plus a prime b, right? That's our standard product rule in calculus. So all right, so again, that's our first step. After we've done that, we need to start pulling all of this apart. So let's remind ourselves again about the Bellman equation. If you remember, the Bellman equation was that the value of some state is the sum over the actions, pi a given s. And we know that it's basically just the q, right? It'd basically be q pi sa. That part I've already written. But q also has a formula, so we can just keep going, right? So it's going to be the sum over the states, next states, s prime, the sum over the rewards of the reward plus discount factor, gamma, value of the next state, because it's recursive, and then the transition probability, right? The probability of actually getting to state s prime and getting some reward r, given we took some action at that state. So this is our standard Bellman equation, and all of this stuff was basically our q value, right? The q value of some state action pair. So if this is q, let's go ahead and plug that into here. We have this term here, and for now we're just going to ignore it, right? We'll kind of get back to this later, and we'll have a shorthand for it later. But for now, let's just keep it as is, just to stay close to the official derivations. Sum over a. We're going to have delta theta, and like I said, we're just gonna rewrite this and ignore it. So a given s, q pi, state action, and then we're going to do plus. We're going to do again the pi. So I'll write it down here so we don't run out of space. It'll be pi theta a given s, and then we want the derivative, the gradient of q, and q is all of this stuff. So let's go ahead and write that out. So it's going to be again s prime r, and it's going to be the r plus our gamma, our discount factor, v pi s prime, and then probability of s prime r given a s. And that's it. And again, there should be a big bracket around all of this, because this outer sum applies to everything inside, right? So because we have a's and stuff inside our expression as well, that sum applies to everything. But I'll not write that over and over again to keep it simple. So there we go. That is our first main step. We just plugged in our form for the q value function. And now that we have that, we can go ahead and evaluate the derivative, right? Let's go ahead and evaluate the derivative. And to do that, let's evaluate it for specifically, this portion right here, and just think about what our derivative looks like. In this case, what is our transition probability matrix? The probability of me getting to some state from some other state taking an action. This depends on the environment, right? This has nothing, remember, the derivative is respect to the theta, and this derivative. Respect to theta. Theta is the parameters of our model. Our model has no control over the environment. The environment sets our transition matrix. The environment sets our rewards. Our own choice is gamma, right? This is our own choice to what discount factor do you want to use? And so our gamma and this probability right here, all of this stuff is just constants, right? As far as the derivative is concerned, right? They're constants as far as the derivative is concerned. So let's go ahead and do a little bit of rewriting. So we're going to have the action, again, pi theta, a given s, q pi s a plus, and then we're just going to do a little bit of distributing. It's going to be a given s, delta theta, and now we're going to, I guess it's nabla, not delta, but that's fine. We have the sum over s, sum over s prime, sorry, r, and then we're just going to distribute. So it's going to be r times the probability of all that stuff on the inside, plus the gamma, our value function for the next state, and then again the probability of all of that stuff on the inside. So there we go. And now that we have that, like I mentioned, this and this are technically just constants as far as the derivative is concerned, right? They're constants. And so we can kind of just not worry about this stuff, because the derivative of the sum is the sum of the derivative, which is the derivative of this plus the derivative of this, which means the derivative of this is just 0 because it's technically just a constant as far as we're concerned. So all we're left with is it's going to be the sum A. We can do, again, just rewrite this because it's just dragging along with everything. SA plus, and then the next term, it's going to be pi theta A given S, right? So there is our, there we go. And then the derivative here, let's go ahead and pull the derivative inside. So we have the double sum over S prime, and then sum over our rewards. And then all we're left with is just this, the derivative of gamma, and then V, our value for the next state, and then the probability of all that stuff that was on the inside. We'll rewrite all that later. Let's do a little bit of a simplification here, though. This gamma value here is just a constant, right? It's just a constant that we set, and we can keep writing it from step to step, but it basically just becomes a scaling factor, and you'll see that later. So just for simplicity, we're just not going to write it because it doesn't really matter. So technically everything's just proportional now, but that's fine. Don't worry about it. We don't care about that too much. It'll just show up again later. So we'll just pop it back in later. So we're left with this, right? We're left with this stuff right here. And we should probably actually write everything that's in here. So this was essentially like we had earlier. It was just S prime R given a S, right? There we go. That is our form that we are dealing with. And so now that we have this, there's one other thing that we can do. Like I mentioned, the R, right, the R's that we see here are technically constants as far as our derivative is concerned, and it'd be convenient if we just didn't have to keep writing it over and over again. So let's go ahead and marginalize, right? So if you remember, if the sum over A of the probability of A and B is just the probability of B, right? We're just marginalizing over one of the terms. Well, in the same way, we have the sum over R, and we have R right here, so we can just get rid of R essentially. If we get rid of the sum, or actually do the sum, then this R term here will just disappear. So this will finally become the sum of A, the derivative of, again, all of this stuff, A given S, Q pi, state action, plus, and then we have the pi, again, action given state, and then we have the sum over just the next state. We're ignoring, or basically we're doing the sum, essentially. We're actually doing the sum, and we'll be left with the derivative of our value function, S prime, and then the probability will just be left with S prime given a S. So we've just summed over that R because the R is, as far as the derivative is concerned, it's just a constant. So because it's provided by the environment, it has nothing to do with the parameters of the model. So we just kind of ignore it, right? Or we just get rid of it for simplicity. That's all. Okay. So now, if you remember, this entire thing, right? This was the value function, or not value, but the gradient. That's what we're computing here. S right here is equal to all of this. And notice the recursion, the derivative of the value function depends at some specific state, right? At some specific state, depends on the derivative of the value function at the next state, which makes sense. The value function was recursive. The way we've always defined it's recursive, so of course the derivative will maintain that recursion. And we could unroll this, right? We could basically rewrite this expression over and over again and try to extract some pattern, but that honestly makes it very, very messy. So we're going to do a quick shorthand, right? We're going to simplify the problem a little bit. The way we simplify this is using a little bit of a different notation. So the notation, and just to give a quick idea, right? Just the unrolling, if you want to see it, is this is the expression we had. We can see the derivative of the values depend on the derivative of the values of the next state. And we know the formula for this. We just plug it in right here and we rewrite it again. And you'll kind of get the derivative of the values at a state is dependent on the next state and then the double next state, right? So 2 states later. And again, unrolling this over and over again will be just messy. So we're going to do a little bit of a shorthand. The shorthand is this. Remember that our original goal is to get around computing our stationary distribution, right? That's what we want to do, and we'll get there in a second. And this distribution, right, the stationary distribution, like we mentioned, comes from just roaming around an environment for a while and then computing the likelihood at being at every state. That's all it was. And so let's say we can represent that entire setup recursively, and that's where we're going to leverage this. So the notation we're going to use is this. Rho pi from s to x, k. This looks fancy. There's nothing fancy. All this is saying, the notation here is, what is the probability of going from some state s to some state x in k steps? That's all. That's the probability. That's all this is representing. So I'm taking k steps to get from s to x. K can be anything. K can be 1 step. So that would be going from s to x in 1 step. K can be 10 steps. That means going from s and doing some stuff and then ending up at x after that 10th step. So we'll kind of see where that comes in just a second. And so a trajectory kind of would look like this. We have some state 1, we'll go to some state 2, go to some state 3, we'll go to some state 4, we'll go to some ... and we'll end up at some state k equals x. And every time we do a transition, we're sampling an action from our policy, right? The policy prescribes the action at a state, so we go ahead and just do whatever the policy says at these things, and we kind of do all these transitions. And so for a single transition, right, a single transition would just be this. It's rho, not p, but they look the same. A single transition is going from s to s prime, right? So from one state to the next state in k equals 1. Well, we know what that is. That's just our standard transition probability. And transition probabilities are just written in the same way as always. We have the sum over actions, probability, basically the policy of action given state times the probability of getting to that next state given that you took that action at that state. And that's it, right? So this prescribes what action to retake, and this is the probability of actually successfully making it to s prime from s given that you took that action. And this is our standard one-step probability, right? The one-step transition. But if our goal is to get to x not in 1 step, but in k steps, there's another way we can think about this. Think about it like this. Let's say that you are told you need to go to the grocery store in 5 hours. In 5 hours, there's this big sale happening, so you need to get there in 5 hours. Does it really matter what you do in the meantime? No, of course not. You can do anything you want as long as on that 5th hour, you are at the grocery store. So another way of writing this is the rho of going from state s to x in k steps is the same as saying the sum over a bunch of different states. We're going to go from rho from s to some other s prime. It doesn't, whatever it may be, it doesn't really matter what it is, in k minus 1 steps. But then in 1 step, we're going to go from s prime to x in k equals 1. And so all this is saying is I want to sum up me going from some state s to some other state, whatever it may be, s prime, in k minus 1 steps. So basically all the different steps I can take, but then on the kth step, the one after this one, I need to go from s prime to my target state x. And that's all it is, right? So this is just a little bit of a trick. And the reason we have the sum right here is because we can go anywhere. So for example, let's say I need to, let's say my target state is this one here. On the kth step, I have to be here. And so that means, and let's say k is 4. That means I can go from here to here, and then here to here, and then here to here. So that's 1, 2, 3, and then 4. That's totally fine. On the 4th step, I ended up here. But that's not really my only option. I could also go from here to here, here to here, here to here, and then on the 4th step, I could end up right here. But there's all sorts of options, right? I could go from here and stay here, and then again stay here, and then again stay here. But then on the 4th step, right, we'll end up where I want to go. So there's all these different ways you can end up. You can even go here early. We can get here first, and then come here, and then come here, and then just go back to here. That's also totally fine, as long as I end up on the target state at the target step. And that's all. That's the notation. So all of this stuff here is basically me doing all of the transitions I want, but I have to make sure the last transition, the very last thing, ends up at my target state. That's all. Okay, so now that that's set up, let's go ahead and go back to our original expression, right? So our original expression, let's just rewrite it here, was basically we showed that the derivative of our value function at some specific state can be rewritten as, can be rewritten as equals the sum over the actions, like we had, the derivative, right? So we didn't really care about this part, so we'll just rewrite it. Again, action given state, and then we have our Q value of the policy of some state action pair, and then we had plus, and this was the thing we spent some time simplifying. We have the, again, policy action given state, and then we had our sum over S prime, right, the next state, and it was the probability of S prime given S A, and we had the derivative as well of the values, the value function, at S prime. And there we go. And so that was the expression, right? That's what we ended up with right here at the end of that, and then we explored that a little bit. Okay, so now that we have this, we know that there's a little bit of a recursion, and actually for simplicity, let's go ahead and just take all of this stuff right here. I should have done this earlier just for simplicity, but that's fine. Let's just rewrite that as phi s, right? So we're going to write that as phi s, and we'll just substitute it back later so I don't have to keep writing it over and over again. So our derivative of the values is phi s plus all of this stuff right here. Now, what we can see is this line right, and actually, sorry, my bad. Let me fix that. Remember, there was a bracket, and that's why I kept mentioning it. Already forgot it. There's a bracket around everything. So this is the same as writing the sum of all of that stuff, right? All of this stuff right here, plus over action, plus the sum of all of this stuff, which is all of this stuff right here. And so really, if we simplify it, if we want to do shorthand, we'll have to do the, not Q, but phi s plus sum over the actions. We need to make sure we keep the sum, right? The sum distributes. And then we'll have pi theta, a given s, and then we'll have another sum, s prime, and then everything we had from before. So probability, s prime given s a, and then our gradient of the value function at the next state. There we go. Okay, so that's our shorthand, right? We have just this, which is just all of this stuff right here. And then because this sum applies to everything, we have to carry the sum over here as well. And now we're good to go. All right. So now that we have that, let's take a look at this system. We have a sum of A times the policy times the probability of that transition, right? We can simplify this more. We can change the ordering of the sum. So let's just switch these two things around just to make it very clear. We have the sum over S prime, and we had the policy, right? Policy. And it was A given S. There we go. And so we know that the sum of the actions over the actions times the policy times the probability of going from some state to the next state, well, that was the one-step transition, right? That was the one-step transition that we mentioned earlier. That's this right here. The policy times the probability of going from some state, taking some action at some state, ending up at the next state. This is a one-step transition. So we can rewrite that exactly in the same way. This can be phi s plus, we have our sum over the next state, that's still the same, and we have our transition. And so this can be rewritten as rho pi from s to s prime, and we're going to do it in k equals one step because it's a one-step transition. And of course, we still have the gradient right here. So derivative theta v pi s prime, right? So there we go. That's the simplification. This and all of this stuff right here is basically our one-step transition probability, right? Nothing crazy. Okay, so now that we have that, we kind of have everything ready to go. And again, remember, all of this stuff right here was the gradient over theta of v pi s. So that recursion is still the same, right? We can see the derivative of the values at some state is recursively related to the derivative of the values at the next state, right? That recursive property still exists. And so because this is pretty straightforward, just because doing writing out the recursion a couple steps here was way simpler than writing out the recursion for all of this stuff up here, let's just go ahead and write it out. So let's just say this is equal to, so all of this is going to be the same, s plus the sum over s prime, the one-step transition from s to s prime in k equals 1 step. But what is this? This is exactly this expression just for the next state. So let's just write it out. This is going to be phi s prime, not phi s, but s prime because it's for the next state, plus the sum over s, not s prime, the next state, but s double prime, so the next state. And then it'll be rho pi. We're going to go from s prime to s double prime. And again, k equals 1 step. And then again, we'll have the derivative right here, v pi, but it'll be for s double prime instead. So essentially, we've rewritten this expression just for the next state rather than for the current s. We've written it for s prime, which essentially just shifts everything over by 1. And now that we have that, we can do a little bit of distribution. So we can do phi s plus, and let's just distribute. So we have the sum over s prime, and we have first rho times phi s prime. So we have phi, and let's actually just keep the ordering the same, rho pi s to s prime, k equals 1 times phi s prime. That's the first one. And then the next one's going to be another distribution. So it's going to be plus sum over s prime, sum over s double prime, right? So we have both of them. And then we'll have a rho pi from s to s prime, k equals 1. And then we have another one, rho pi s prime to s double prime, again, k equals 1. And then, of course, at the very end, we had the this term, the derivative. So value pi for s double prime. But do you notice a little bit of a simplification we can do right here? Notice that this is the transition from some state s to s prime in 1 step. And this is the transition from s prime to s double prime, also in 1 step. Well, that's the same as just going from s to s double prime in 2 steps, right? That's an equivalent thing to say. So let's go ahead and write that out. And so this is going to be equal to, let's see, right here. Okay, yeah, so we can just merge all this together. And so this is going to be equal to the s plus the sum over s prime rho pi s to s prime. And this s prime right here, we're going to avoid writing it again. We're just going to say that this outer s prime applies to everything on the inside, right? Just to keep it simple. So it doesn't really matter because the sum would distribute to all the internal sums, right? So we'll write it out that way just to keep it simpler. So we have this s to s prime in k equals 1 times phi s prime. And then the next one was plus, again, the sum s double prime, right? S double prime. And it's going to be rho pi s to s double prime in k equals 2 steps. And again, we have our derivative, right? Derivative, just like before. And that's going to be v pi s double prime. Nice. And so this is, you can already start to see a little bit of a pattern, right? You should be able to start seeing a pattern. If we wanted to do 3 steps, well, we could, again, take this thing here, expand it out, basically distribute all of this stuff to those terms, and then resimplify. Just do exactly what we did, just do it again. And so you'd end up with something like this. So you'd have phi s plus the first, and actually I don't need to rewrite it again. We'll just add the next one. It'll be plus, if we did it again, all of this would disappear. It would become phi s double prime, right? Just like that. And after we did that, we'd have another sum from s triple prime, right? Triple prime. So 3 steps later, from rho pi, from s to s triple prime in k equals 3 steps, and then it'll be not phi, but this will again be the gradient, right? So it'll be the derivative of the value function at s triple prime, right? And this whole thing will just keep continuing on and on and on. So technically we can just write this would become phi s triple prime plus dot 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 dot, right? It'll just keep going as we continue to unroll that recursion. And so now that we have all of this, it seems like a lot, but it's all gonna, we can write it all in one condensed form just to make it simple. This first term right here, phi s, we're gonna do shorthand of, we're gonna say that rho from some s to s prime in k equals 0. K equals 0 doesn't actually mean anything, so we'll just call this 1, as in, like, of course we can go from something to, I guess it'd be itself, right? Something to itself in 0 steps is technically just 1. It doesn't matter. So that's just a little bit of a simplification. But if we say that, then we can write essentially this. We can say the derivative of our value function at some s is basically the sum from over x, element over, all the states. So sum over all the different states that we have, and then sum over k equals 0 to infinity of rho pi s 2x in k steps, and then phi x. And that's all it is. That's all it is, right? We're basically doing what is the probability that starting from some state s, we end up at some other state x in all the different k steps that we can take, from 0 steps all the way up to infinity steps. And that if we again rewrote, if you wrote all of this out, you would end up with just this expression that we had up here. So this is essentially our final expression for the derivative. And notice that we just took the derivative, but we never had to deal with the stationary distribution. Notice that the d, right, d pi s, never showed up. And that's the key thing about this derivation that we're trying to avoid. But that d pi s is in this expression. We just have to compute it, right? It's here, and we're going to unveil it now. So now we're going to go back to the notation of the book, right? The way the book says this essentially is write it like this. We're going to say that the derivative of j theta is just equal to the derivative of, again, with respect to theta, of v pi s0, or some starting state s0. And you might be asking, like, oh, how's that possible? Where's d, right? Where'd the d go? And d is actually in here. We're about to extract it. So let's go ahead and take a look. We said that all of this is equal to, the way we wrote it, is going to be the sum of s element over s, and then the sum over k equals 0 to infinity, right? How many steps of transition we want to do. We can go from 0 steps of transition and sum up every iteration up to infinity steps of transition. And we have rho pi s0 to s in k steps. This is what we just wrote earlier, right? So nothing fancy. There we go. And as a shorthand, just as a shorthand, the books calls all of this stuff right here. All of this stuff, they call it, I forgot what that symbol is called, but there we go. That's what they call it, just to make sure that when you look at the book, everything makes sense. Okay, so if that's the case, then we can, again, simplify this one more time. This is really just the sum over s element of all the different states we could be in times this times our phi, and we're good to go. And essentially the way you can interpret this, right, or all of this stuff up here, is that it's essentially just an accumulation, right? It's an accumulation of all the transition probabilities over infinitely long trajectories, right? Because this is basically the sum of a 0-step trajectory plus a 1-step from 0 to s, 2 steps from 0 to s, 3 steps to 0 to s, so on and so forth. And in the end, it basically says, if you sum all these up, or maybe another way to explain this is, you have all of these different states, and let's say this is S0, this first one, and let's say S, right, we're going to sum this up for every single S, but let's just pick one of them for now. And let's say we pick this one out here. And so the question is, what's the probability of going from S0 to my target state S in 0 states? what's the probability of getting there in one state? Probability of getting there in 2 steps, 3 steps, 4 steps, 5 steps, infinity steps. Right? And you can imagine, right? There's so many ways to get here. If I want to get there in 0 steps, well, that's not possible. 1 step, well, whatever the transition probability is for that 1 step. 2 steps, well, we can go here and here. Or we could go here and here. Or we could go here and here. Or we could go to myself and then here. Like there's all the different probabilities, which is why we'd be summing them up, right? We'd be adding them up. And then what about probability of getting there in 3 steps, 4 steps, 5 steps, infinity steps, so on and so forth. And that's basically what this is. We're computing all the different ways, right? It's a sum because it's or, because we can go from here to here in 1 way or 2 way or in 3 steps or 4 steps or 5 steps. And in the end, you end up with what's the probability overall of getting to some state S from some state S0 in this specific environment, right? So it's essentially the accumulation of transition probabilities over infinitely long transitions. Now, this value on its own is fine. It's going to be some probability, but it's a little bit less helpful in the sense that I'd like to have a probability distribution over the states. And so the way we can do this is just a simple multiply divide setup. So what we're going to do is so each one of these is basically the accumulation of getting from some state S0 to S, right? That's all it is, the accumulated probability. But what I want overall is the probability of getting to any one of the states S. So let's draw this back again. Let's just put this back how it was. Should have left it. What this tells us is what's the probability of getting from some state S0 to some other place in all the different possible number of steps of getting there. And that's fine. But what I really want is what's the probability of being at this state or at this state or at this state or at this state or at this state. Right? That'd be more convenient to have. And so let's just normalize it essentially. What we're going to do is we're going to take S element of S of here. Basically, you can imagine these all, let's say we have getting from S0 to here is like 0.8, and S0 to here is 0.3, and S0 to here is 0.7, and S0 to here is 0.2, and S0 to itself, let's say 0.1, whatever it may be. Now, what we can do is we can normalize it so all of this stuff adds up to 1, kind of like softmax, right? You probably could have done a softmax here as well, but we just do a simple, just add it all together and divide by the total. So the sum of all of this stuff would be 0.1 plus 0.3 is 0.4, plus 0.2 is 0.6, plus 0.7 is 0.13, plus 0.8 is, it'd be 1.3, and then we'd have 2.1, right? Yeah, 2.1, if my math is correct. So then we go back and just divide each of these things by 2.1, or whatever the total is. 2.1 divided by 2.1, and then this will make sure that all of these probabilities add up to 1, so it's just a little bit more helpful. So basically, here's the sum of all of those things. That's me doing 0.1 plus 0.3 plus 0.2 plus 0.7 plus 0.8, and then we just multiply that by we had the other sum, S element S. We had our S divided by, again, that S element S. So there we go. Because we multiplied by something and then divided by the same thing, we're not breaking any rules, right? We're not breaking any rules. So that's it. We're just simply normalizing it. So our total probabilities add up to 1. So instead of saying this is the probability of getting from some state to this other state, it's more saying what's the probability of ending up at any one of these different states. And we also had the phi S here already from before, which we can't get rid of. And so that's it. That's all we've done. And technically, right, this and these are just constants, right? The sum of these or the sum of these are just constants. So we can just kind of ignore this one because it's just a constant, and we want gradients anyway. And so the maximizing a gradient or maximizing the gradient times a constant are the same thing, so we don't really care about it. So it's proportional essentially to S element S over the sum of all of those. And there we go. And we had the phi S as well. Well, what does this look like? Let's kind of think about this expression right here. Each of these things end up being the probability at ending up at some state over some infinitely long trajectory. And so let's kind of think about it this way. So this is the probability from elements of infinitely long trajectories in our environment, and the distribution weights the likelihood at being at different states, right? By dividing this, we're basically the likelihood of being at one state versus another one versus another one. Isn't that essentially D? Like, isn't this exactly what D is supposed to be? Because D was, what's the probability of being at one state versus another one versus another one versus another one over long trajectories, right? Long horizons. And so if that's exactly what we have here, then this is D. This is exactly what we want. This is exactly D. And so our proportion here is just a probability over the states. And this probability is constructed by just normalizing the probabilities of infinitely long explorations of the environment. And so it's exactly the stationary distribution that we've wanted, just without actually having to do the derivative. So that's really neat. It's really neat that the stationary distribution ended up showing up in our derivation, and we never had to explicitly take the derivative of it. And this is exactly the trick. This is exactly the trick of our derivation of policy gradients. And so finally, what we end up with is the sum over state, all the different states. We have our S phi S. Like, this is the aha moment, essentially, for this derivation. So there we go. We now have that. And of course, we had phi s is just we just wrote it. So let's just actually write it out again. So again, this is going to be sum s element of s d pi s. And then phi is essentially just going to be the sum over the actions. And like we had before, it was the theta pi theta action given state. And then we had our Q values, S, A, right? That's our, what that expression was. And so technically we are done. This is actually the form. This is one of the many forms for the policy gradient theorem. But if you look online, this is actually not the form you'll typically see. There is one more step that they do. And basically, we're going to do the same trick again. We're going to multiply and divide by some constant. We're going to multiply and divide by pi, by our policy. So let's just do that. So it makes it very clear of what's going on. You could stop here. I mean, you could solve reinforcement learning problems using this. It would be fine. But let's just make it look like the official definition. So let's go ahead and do, we'll have our Q pi S A, and we're going to multiply by the policy of A given S. We had the derivative of some policy, theta, A given S, and then we're going to divide by the policy of A given S. Sorry, my math became a little lopsided. That's okay. No one's going to mind. But we just multiplied and divide by a constant, right? So it doesn't break anything. I'll write the next line more straight. S element of S, d pi S pi A, Q pi S A. And because we multiplied and divide by a constant, again, it doesn't affect anything. And let's kind of think about it this way. And actually, we don't need to write this term again. Let's write it this way instead. We're going to just put the sums together. So you have the sum over S. We have the sum over A. We have our stationary distribution, right? The estimate of our stationary distribution. We have some pi, A given S. And we have our Q pi, S, A. And then we have our derivative of pi theta, A given S, divided by pi, A given S. There we go. And what does this look like to you? Let's remind ourselves in expected values, right? So if we do the sum of the probability of x times f of x, well, that's the same as writing the expectation over p of f of x, right? That's our expected value formula. Well, we don't have one sum here. We have two of them. We have a sum over s, sum over a. We have the distribution over our states. We also have the distribution over the actions for that specific state. So technically, we can just rewrite all of this as just a big expected value over our state coming from the state coming from our stationary distribution, the action coming from our policy, and this is going to apply to Q pi S A times the derivative, again, of pi theta, A given S, divided by pi of A given S. right? There's nothing wrong with writing that. That's totally fine. So it's just a, we're just expressing it as an expected value. And technically, both the state and action we want to go to, it all kind of just depends on the policy, right? The policy determines everything. So we'll just go ahead and just write e pi as shorthand, right? That's the notation they typically use. But really, it's two different things. There's the state from the D, and then there's the action from our policy. But again, we're just sticking to shorthand here. And this is almost the derivation, final form that you see. But there's one other thing we can do. Remember, the natural log of the natural log of some function f of x, the derivative of that is just the derivative of the inner function divided by f of x. That's our standard chain rule setup, right? Let's just go the other way. What we have is the derivative of a function divided by that same function. Well, that's the derivative of a function divided by the same function, which means all we need to do really is just write it like this. So final form, expectation over pi q pi s a. And then instead of writing it as a fraction, we're just going to write it as the derivative over theta of the natural log of pi theta a given s. And this is officially the final form that you'll typically see. So you saw this derivation was not terribly challenging, just a little bit of mathematical manipulation. But again, the key idea is we wanted to avoid computing this as much as possible. This is impossible to compute. But we saw that by setting up our derivatives in the correct way and actually, simplifying the expression in some fun algebraic tricks. Sorry for my math being a little lopsided. That's always fun. We saw that the stationary distribution kind of unveils itself. We're able to reinterpret what we're looking at here in terms of the stationary distribution. And that's the key idea. We have the stationary distribution built in to our gradient here, but we never explicitly took the derivative of that stationary distribution. Remember, the stationary distribution is technically just a constant, right? It's a constant because it's essentially, it's a constant for a specific policy. The expensive part is for every single policy, it needs to be recomputed, which means every time we update our neural network, we need to recompute our stationary distribution, which is again, basically impossible for any significant continuous state problem that we're working on. Maybe in some dummy cases, it wouldn't be too bad, but for interesting problems, it would not work. Good, so that's it. That is the policy gradient theorem. So let's go back to the slide deck. Go back right here. And so this is what we ended with, right? We ended with this right here. But you could be imagining, my promise at the beginning was that, hey, let's not compute, let's go back right here. Let's avoid computing Q values. We don't want Q values. We want to cut out the middleman. What we want is the policy directly. But as you see in our policy gradient theorem, we kind of have Q values right here. So we haven't gotten rid of them yet. And that's why a bunch of different algorithms exist to estimate the Q values without explicitly computing them. The main first one we'll be looking at is the reinforce method. The reinforce method is a Monte-Carlo policy gradient estimation of your Q values. I have a whole video dedicated to Monte-Carlo learning. So you can go ahead and take a look at that, and we'll essentially just be using ideas from there. Monte-Carlo, the idea was essentially, okay, so we'll go back a slide. In Monte-Carlo, the main idea was that we want to compute these returns GT. And the returns are basically what are my future rewards. So at 5, my reward for getting 6 is my reward at getting 6. My return at step 5 is my future reward. So it's whatever reward I get at step 6. My returns at 4 is going to be the reward I get at 5 plus discounted reward I get at 6. My returns at 3 is going to be whatever reward I got at 4 plus discounted at 5 plus discounted at 6. What are my returns at 2? It's whatever reward I get at 3 plus discounted at 4, discounted at 5. You see the pattern, right? You see the pattern. It's very clear right here. And this was actually the very first thing that we did, right? And when we derived the Bellman equation, this is kind of where we started, right? It was basically the expectation of GT that we use to solve for our setup. And so the reinforce algorithm just uses this. What we're going to do is use our GT to estimate our Q values. Because remember, our value function, the values of a state, the value of some state, is my expected value of the GT at that state. Well, my Q values are going to be the same thing, but instead of just being the expected value over which state I'm on, it's going to be for every state action pair. Simple as that. So we'll kind of see all that come together. Our neural network, instead of predicting Q values, so instead of doing Q, it's going to be a policy, or it's going to be a policy, which means that it will be predicting probabilities, right? What's the probability at this state I should take action 1 versus 2 versus 3 versus 4? What's the probability? One other thing is Monte-Carlo requires us to play. So again, the entire point of Monte-Carlo is we essentially play a game. We collect some trajectory information as we go. We use the trajectories to compute some GT. And in our initial Monte-Carlo method that we had learned earlier, all we did is we cared about the final, right? What was my final return? Basically from state 1, what was my final estimated return? What we need now is not just the final one, but all of them, and how all of them contribute to my overall trajectory. So we're going to do the same thing, but we're going to compute the returns at every single state and then add them all together, right? We're essentially just going ahead and seeing the contributions to GT across all the different time steps of our trajectory. That's important because our neural network needs to be able to essentially decide what action it should take at every step based on the information it gets at all the different steps, right? Not just the last one. And so there we go. That's one trick that we're going to have to use. Another trick is G can be a very noisy, it can be a noisy estimate, right? Especially at the beginning of training, right? When the model doesn't really know what it's doing, G can change wildly, right? What are my returns can change wildly, especially over long horizons. If we have long problems, there's a lot of opportunity for variance, right? Across these trajectories, right? A lot of things can change. There's a lot of randomness in a system. And so we need just a way to help. One typical way is if we have some trajectory of G's, so I called it some vector G, we're going to go ahead and standardize it. Subtract the mean, divide by the standard deviation. This seems to help with stabilizing training, just a small trick that we'll toss in. The main reason for this is because we no longer are training on batches. Remember in Q-learning, in deep Q-learning, what we did is we had some replay buffer. We collected a bunch of samples, then we randomly grabbed a batch of samples from the data from our replay buffer, and then we trained on that. We no longer have that. We only train on one trajectory at a time. And this is why it's important for us to go ahead and do any kind of effort possible to stabilize training, because especially at the beginning of training, when the model doesn't know anything, these will be very bad estimates, right? Next thing, exploration versus exploitation. If you remember again, an important part of reinforcement learning is to make sure, at least at the beginning of training, we spend a little bit of time exploring the environment. Because if you don't explore the environment, then you don't really know what are all the possibilities. And so one thing we can do is, because we have a probability distribution at the output of our model, the closer our output distribution is to uniform, right? So if it's uniform, if there's 4 options, each thing has a 25% chance of happening, then that means you're essentially randomly selecting, right? Everything is random. And entropy is maximized at uniform. So uniform distributions have the most entropy possible because it's the most random possible. And so that's all we're going to be doing here. We're just going to go ahead and compute the entropy and add a slight entropy penalty. So there's no longer the idea of just take a random action 10% of the time and follow the policy 90% of the time, like we were doing on the epsilon greedy strategy. But now it's just going to be, to our neural network, we're going to add a tiny little penalty to make sure that the outputs of the neural network are slightly uniform, right? And it won't be. Of course, there's a lot of ways to do this. The constant we use to kind of say how much weight we want to put in this can be tuned or decayed over time, where at the beginning we want lots of emphasis to be uniform, so there's lots of random selection. Over time it can decay. You know, there's all sorts of little tricks we can do, but for the simple environment that we're working on today, we probably don't need to worry about any of that. Okay, so that is it. All right, oh no, you cannot help me actually. There we go. All right, so let's go ahead and implement it. Right, so let's go ahead and implement it. We have all of this. We went through all of these derivations. Okay, good. All right, step 1. We need a policy network. This network is going to be very simple. Of course, import torch dot nn as nn. Oh, and just to recap, these are the same imports as before, right? Nothing fancy. I already imported. It's fine. Okay, so the same imports as before, and we have Gymnasium, right, where we'll be playing like always, our lunar lander game, just because it's simple and anyone can do it very quickly. Class policy network, and then dot module def init self, and we're gonna have input state features is 8, right? So there's 8 input features in the lunar lander game. Num actions, there's 4 different actions I can take at everything, and I'll just do some hidden features is 128, right? Super.init, and we'll do self.fc1 is a linear layer that's going to go from input state features to hidden features, and then self.fc2 is another linear layer that's going to go from hidden features to hidden features, and then self.fc3 is again another linear layer that's going to go from hidden features to our final num actions. Self.x, we're going to pass in some actions, and then this will be pretty straightforward, right? X is going to be equal to f.relu self.fc1x. Go ahead and just, add some activation function. You can play with different ones. We're keeping it simple. Self.fc2 x, and then x is equal to self.fc3 x. But this on its own isn't enough, right? What we want isn't the logits, but probabilities. So to compute probabilities, we can do pi is equal to f.softmax x, and then dim equals -1. So we're going to compute the softmax along the last dimension, so along the action dimension. So we have 4 different actions in this case. So what's the probability of those different actions? That's all. And we return pi. Did I miss a comma? There we go. There we go. All right. Very simple, right? So it's the standard. It looks just like the networks we've written earlier. It's just now we add this extra softmax because we're not estimating some value like the Q value. What we want is the probability of the different actions. And there we go. All right. Next, we need to be able to compute a trajectory, right? So we can do def compute trajectory. We need the reward trajectory. So this is going to be a list of numbers that tells us the reward that we got at every step along the game. And then we need some gamma, right? I'll just pick 0.99. That's fine. Which will be our, Okay, good. So now we have returns is an empty list. GT is initially 0. And we'll do for RT in reversed reward trajectory. So the reason we are reversing, so reward trajectory, is mostly because it makes it easy to compute, right? So we don't have to recompute something over and over again. Notice that our rewards will be in the order of 1, 2, 3, 4, 5, 6. But we know that G5 is R6. And we know that G4 is R6 times our weight plus R5. And then we know that G3 is going to be R6 times a weight plus, okay, here we go. So G4 is R6 times gamma plus R5, which is the same as just saying G6, which we had earlier, plus R5. So we're essentially working our way backwards. Again, when we do G3, and actually this is slightly incorrect. This should be not G6, but G5. Okay, I'm not logged in right now. That's fine. That's fine. This should be G5. And then G3 is going to be R6 times gamma squared plus R5 times gamma plus R4, which is just taking G4, which is R5 plus gamma R6, multiplying G4 by gamma, and then adding it to it, the new R4, right? So you can see we're just working our way backwards. So as long as we have R6 first, then we can compute R5 times gamma R6, then R4 plus gamma G4, which is R4 plus gamma R5 plus gamma squared R6, ... right? We just repeat that over and over again. Otherwise, if we went the other way, then it'd still be fine. It would give us the same thing. But we'd have to basically do the whole trajectory 1 through 6. Then we have to do it again 1 through 5, 1 through 4, 1 through... It's just less efficient, right? So going backwards is a little bit more efficient just because of the recursive nature of this. So we're going to do in reversed. We're going to do GT is going to be... GT is going to be just RT, the reward we got at that step, plus gamma times GT. We're going to keep updating that over and over again. But because we are going in reverse, we can't just append. We need to always prepend. So we can do dot insert 0 GT. So we essentially, as we save in the list, we don't keep appending over and over again. We just prepend it over and over again. And that's all. We could have also just appended it and then reversed the list. That would have also been fine. And then we can return torch.tensors, or tensor returns, and then dtype is just, let's make sure it's a torch.float32, and that should be good. And that's it. That's us computing the trajectory, right? Computing our return trajectory. So we played a game, right? 1 through 6, and then we just iteratively compute what the GT is at every single one of these states, and that's all. And we just store them, prepend them. Okay, training script. This is pretty straightforward. It'll be way more straightforward than any other training script we've written so far. So it's going to be def train. We're going to take an environment. We have our input. Actually, I'll just copy this line right here, so I don't have to type all of it out. But we have a couple of different things. We have this is our model definition. We have our neural network learning rate. How many episodes? How many games do we want to train for? This is just a running average for printing purposes. We have our how often do we want to print, our gamma. This is the weight for our entropy penalty. So we incentivize the model to at least stay a little bit uniform, so it's always randomly doing something. More typically, you'd not have a constant entropy penalty, but it'd be something high initially and then decay over time. And then we have our device, whatever we want to train on. So our policy network is going to be the policy network. There we go. Oh, there we go. Input state features is going to be input state features. We have our num actions is num actions, and then we have our hidden features is our hidden features. And we'll just make sure this is on the correct device. Good. We need an optimizer. We'll just use Atom to keep it simple. Atom model dot, or it'll be policy network dot parameters. Learning rate is going to be whatever learning rate we set. And then let's just go ahead and create a quick log here, just so we can store stuff for printing scores. So what is my score? And then of course, because it's noisy, we'll do an average, just so it's easier to see. Running average scores. Again, empty list. We'll store results as we play. And so let's just say for I in range episodes, so how many games we want to play, state blank, we don't care about the info, is equal to env.reset. That goes ahead and starts a brand new game. Now that we start that, we're going to store a bunch of stuff. We have our log probabilities. Why are we doing log probabilities? It's because, remember our loss function right here, log probabilities, right? Because policy is probability, so we want log probabilities just for simplicity. So there we go. So we have log probabilities. We're going to have our rewards is an empty list. Our entropies is an empty list, and done is false, right? So we can tag the end of the game. So we can do while not done. First, let's grab our state. So our state is going to be torch.tensor. It's going to be the state. Dtype is dtype is torch.float32. We're going to add the batch dimension. So it'll be 1 by 8. Remember, it's just one time step at a time, so it's 1 by 8 dot to device, or 1 by however many, however many input state features there are. There's 8 in this case. That's our state. And now what we're going to do is take the state and pass it through our model. So action probs is going to be equal to the policy network, and we're passing the state. And this tells me what is the probability of the different actions I take at this state. And now we need to select an action. So we can do selected action. We can do torch dot, let's just randomly sample, right? Multinomial. Because this, again, sampling is what helps with making sure we're exploring the environment, right? So we can do multinomial action probs. And num samples, we just want one dot item. So it'll give me the index, right? So in this case, there's 4 options, so 0 through 3. It's going to be one of them, whatever action we took. And our log prob is going to be torch.log of the action probs There's only one sample, so its index is 0, right? It's because it's 1 by 4 in the output. And then selected action. We're essentially just indexing out what is the probability of the action that I randomly selected here, and then I take the log of it. So I have the log probability. That's all. And of course, we have our little entropy term. That's going to be negative torch, standard entropy formula, negative torch.sum. It's going to be the action probs times torch.log action probs. And just for good practice, if we're doing a log of something, we should add a little term to it so we don't throw an error, right? There we go. So we don't like take the log of 0 or something. That's just a little entropy term. That's all. And now that we've selected an action, it's time to actually take that step in the game. So we're going to do next, state, reward, terminal, truncated, and then everything else we don't really care about, env.step, and it's going to be selected action. And that's it. So all we've done, just to recap, right, we took a state, we have a state in this game. We go ahead and apply our model to the state, get our probability over the action. We randomly select one of those actions based on those probabilities. We get the log probability of the action that we took. We get the entropy just to make sure we can add that penalty in a little bit later. And then we have our us taking the next step in the game. And now that we've taken the next step, what we're going to do is just store some of this information for this whole game. So log probs dot append log prob. We have our rewards dot append our reward, and then we have our entropies dot append entropy. There we go. And we can do our quick check. We are done if it's terminal or truncated. So if we're at the end of the game, or if the game's gone on for too long, then the game's done. And then the state is equal to the next state. There we go. And so now, once the game is over, it's time for us to compute our returns, right? So the returns is going to be equal to the compute rewards method that we just wrote earlier. It's going to be rewards with whatever gamma we picked, and make sure it's on the correct device when we do that. And there we go. Nothing too crazy, right? We've completed a game. We've stored up a reward trajectory. That's basically what we have right here. At every single step, we stored our rewards, and now we're going to use our return formula to just compute the returns of 5 for 4, which is reward at 5 plus discounted at 6. Reward at 3 is the return at 3 is the reward at 4 plus discounted 5, discounted 6, right? We just do that over and over again. So there we go. That's us computing the returns at every single step. And like we mentioned, these returns, especially along long trajectories, can be highly noisy estimates. So something that typically helps with stabilizing training is to normalize them. So we're going to do returns minus torch.mean returns, or let's do keep it shorter, returns.mean divided by returns.standard deviation, and we'll do a plus 1 e negative 8, so we don't divide by 0 by accident. And there we go. And then our loss is going to be equal to, and this is it, right? This is everything we've worked up to, is this loss function. It is this loss function right here, or actually right here. We're going to go ahead and do the returns times the log probabilities, and then we're going to go ahead and just sum it up across all of the different time steps that we have, so we get the contributions from the different time steps. So it's going to be negative torch.sum. And actually, I never mentioned the negative, so we want to maximize, right? Of course, our typical setup is we want to maximize the returns. Neural networks don't maximize, they minimize. At least that's the default setting for the Atom Optimizer. So instead of trying to maximize this thing, we minimize the negative of it, right? So it's the same thing. So that's why we have a negative right here. We have a sum, and that sum is this sum right here. We're going to sum up all of those different contributions. And we're going to do torch.stack log probs times returns. And that's it, right? All we've done is we have our returns right here, a vector of returns. And then we have a vector of log probabilities, right? Vector of log probabilities. And that's been stored from here, right? We've been storing them as we've been going. So we just stack them together to create a vector of log probabilities for every single step along the game. We have the returns for every single step along the game. And so we just go ahead and multiply those two things together, and then we sum over all of them. And that's it. That is our loss function. All of that effort for that, and that's all. All right. And of course, we need our minor penalty for the entropy. So entropy, we want to maximize entropy, right? Because more entropy means more random. So we're going to do minus entropy weight times, right? So it's negative rather than plus, but that's fine. It just flips it. And then we have torch.sum, torch.stack entropies. What was the entropy along every single step in the game? Go ahead and make a vector, add up the entropies, and then we do minus entropy weight, so we flip the direction. That's all. Good. And so now we can do optimizer.zeroGrad, and then loss.backward, and just for good practice, we can do torch.nn.utils.clip grad norm, policy network.parameters, max norm is 1.0, right? Just to make sure we don't have any exploding gradients, and then we do optimizer.step, and we have officially updated our model. Our total rewards is going to be sum rewards, right? So this is the total reward we got along the entire game, right? So we can go ahead and add it all together. And then let's just store everything. So log scores dot append total rewards. And then our running average score is going to be np.mean log scores. And we're just going to look at the last negative running average steps, right? However many we wanted. Just go ahead and grab them, average them together, and our log running average scores. And we're going to do dot append running average score. And there we go. I'll print this right here. We'll just throw that in there. So, every however many steps, go ahead and print it out. And then if our running average score is greater than 200, which means the last 25 steps, the average score is more than 200. 200 is our success condition for this specific game, the Lunar Lander game. So that's what we're using right here. And then we can return the policy and the log. And so just to play the game, very simple. We're going to go ahead and just play the game. Let's see if there's any bugs. Compute rewards is not defined. Should be compute trajectory. Not bad. Actually, it should be compute returns, right? What am I calling it? Yeah, whoops. This should be first compute returns, and this should be compute returns. My bad. All right, so yeah, we can see the game has started. This doesn't take too long. It takes about 5,000 steps to get to the success condition. That's fine. So we'll let this play for a second. It's less interesting to watch that happen. So here you go. It'll kind of end up looking like this. We could probably let it train longer. We can probably be a little bit smarter about how we do our our entropy weight and stuff like that. But overall, we can see the model's like learning something reasonable from bad scores to reasonably okay scores, and we end up with something like this, right? So it'll end up, playing the game just fine. Ta-da! So yeah, that's basically it. The entire point of the policy gradient network that we've seen here is that we can now compute the derivative of our policy directly. Notice that we've been able to represent, and this is the key idea, we're able to represent the cost function, the thing we want to maximize. We can represent it as the derivative of the log probabilities produced by our policy model. And there's no longer some Q value, some internal Q value that we're first trying to estimate. And then after that, from the Q values, we derive our policy. So there's no longer this step of train a model that does the Q values, and then after we train the Q values, go ahead and train some, grab the max if we're doing greedy to actually get the policy. None of that exists anymore. We're able to directly train the policy, which is awesome. During inference time, we're just doing argmax. So we're doing greedy estimating, or basically greedy estimates, just like we've done before. Grab the action that has the highest probability. Rather than something with the highest Q value, now we're grabbing the action with the highest probability. And that's basically it, right? That's the key idea behind our policy networks. This only opens the door to policy networks. The reason I wanted to focus on this is because there's a bunch of little things we need to do regarding policy networks. The main ones is the proximal policy optimization, the PPO algorithm, and then its prior TRPO, trust region policy optimizations. All of that's already in my Git repo if you want to get a head start. But PPO especially is the bedrock of the RL algorithms applied for large language models, which is the entire purpose of all of these tutorials anyway. We want to get to training LLMs with reinforcement learning, but we can't really do any of that until you actually understand what's going on, right? So that's it. It's a little bit of a long one, so if you made it this far, great job. I'd go through that derivation once on your own. I think it's just important to have. But I'll call it here, and I will see y'all in the next one.